Welcome, ladies and gentlemen, to PASCO Laboratories. It's so nice to have you with us again this week. I'm JP, and many people ask me, what does the P stand for? Well, this week, the P stands for party. And not just any party, because this week is a very special mole party. That's right, we're having a mole party here at PASCO Laboratories because tomorrow is 10/23. Tomorrow is 10/23. October 23rd is Mole Day. And why is 10/23 Mole Day? Because a mole is 6.02 times 10 to the 23rd. Now, this is a very, very important concept in chemistry, an extremely important concept really for all things that we teach in chemistry. And what we're going to be showing you today are some great things that you can do at home, that you can do in the lab. And if you stick with me to the end, I'm going to give you a really great promotional opportunity for you. And remember, ladies and gentlemen, we are live, and so please write in and say, hey, I've got a question for you. Or anytime throughout the week when you're watching this, you can drop me an email. My email is here for you at jkeener@pasco.com. We love your emails, and almost every week we select an email for our show. But this week, we are doing a special just because 10/23 Mole Day. And to help me celebrate Mole Day, we are bringing in a couple of experts, and we're going to start with a mole expert, Barbara. Welcome, Barbara. Nice of you to help me celebrate Mole Day. And Barbara, why is mole so important?
Moles is how chemists count very small things like atoms, and it also helps chemists figure out how much stuff to put together in a reaction so they don't waste anything.
So when you say reactions, and of course we know chemistry is all about reactions. Everything that we do in chemistry is reactants, products, and that ability to measure those really comes down to the mole concept, doesn't it?
That's right, and so grams, moles, all those conversions that you do, we've got some great demos to show you things with the balance, things with sensors, and ways to count without actually counting out individually 6.02 times 10 to the 23rd things.
Because that's a big number, so big that when we talk about it with our students, we try to imagine what that would be like with something like marshmallows.
Yeah, marshmallows. So there are, if you had 1 mole of marshmallows, 1 mole is 6.02 times 10 to the 23rd marshmallows. That would cover the entire United States to a depth of 6,500 miles.
6,500 miles of marshmallows, and that's a mole. So of course we don't use moles when we talk about marshmallows because that's certainly more than we would have or need for our party, but we do use it when we're talking about atoms and molecules because they are so very small, and so that's a perfect measurement. And so today we're going to show you again some things you can do at home, some things your kids can do at home, some things that you want to do, and if you stick with me till the end, and let me just give you this little get ready, I'm going to give you 5% off some of the great things that you're going to see on the table today. I'm going to give you 5% off, but stick with me to the end, and I'm going to show you how that's going to happen because right now it's time to party. And when we party, it's time to bring in our own mole master, Roger. Roger, come join the party.
Ain't no party like a mole party. Let's get this party started. All right, what do we have here today?
Well, let's take it. So JP was talking about marshmallows and how it would take 6,000, it would be 6,500 miles deep with marshmallows if we had a mole of marshmallows in the US. But how about instead of marshmallows, let's count a mole of atoms.
Let's do it.
Count a mole of atoms.
As a matter of fact, we have a set of materials that can describe that set of atoms. And really, scientists picked a mole because they wanted a sort of workable amount. Can you imagine having some kind of scientific apparatus like a beaker and you wanted to put a set in there? Well, this is 1 mole of aluminum. Aluminum is an element, and it is in the periodic table. You might be able to see that right here in the periodic table. But you may ask, how in the world do we know you have 1 mole? And instead of saying, I'm going to count these, which would take forever, we're going to put this on a scale. So let me put this on this scale right here.
And we've got this balance wirelessly connected to SparkView so that you can see the mass in SparkView. You could even record it if you'd like.
Right. And if you pick up a periodic table, while this is simple so you can see this example of our periodic table on the desktop here is there. Usually you'll see a number that's right underneath this, and non-coincidentally, that number is going to match exactly what we see 1 mole weighs on the scale. The atomic mass on the periodic table ends up being the same as what 1 mole would weigh, and that makes it far easier to count out that number, 602 hextillion particles in each of these sort of cubes.
So that is 6.02 times 10 to the 23rd atoms of aluminum.
Yeah.
This is not 6,500 miles deep. This tells you how small an atom really is. There are that many in this little block.
Crazy small. We'll pick one more example right here. This, you can tell, looks like a penny. So it's made of copper. If I put this on, I'm going to put it on the scale. And if we look in the periodic table, we should get around 63.5, exactly where we're at. Maybe a little less. Or that looks really good. And it's the same as that atomic mass. And so these are just convenient sizes for chemists to work with.
Yeah, it's easy to visualize a mole too of how small atoms are when I look at these. This is our mole set, and you can get this at PASCO.com.
Now, what about a liquid, though? Would that be something similar? Not even, I mean, just elements, which aren't here. There's not too many elements that are liquid. So let's go to a compound, like water, for instance. Could you give me an example of what a mole of water would look like?
Well, a mole of water, now you're not just talking about one atom, you're talking about 3 atoms chemically bonded together, H2O. 2 hydrogens, so you would get the mass of 1.01 from each hydrogen, multiplied by 2, 2.02, plus the mass of oxygen, 16. That gives you 18.02 grams for every mole of water molecules.
And that's what this is.
Because water's density is 1 gram per milliliter, that means milliliters and grams are equivalent for water.
Fantastic. So really, 18 mils of water is a mole as well. That's about the same. Again, a workable amount, and that's what chemists were looking for, nice workable amounts in the lab.
Okay, so 6.02 times 10 to the 23rd molecules of water. So we've seen a solid, we've seen a mole of a solid, we've seen a mole of a liquid. Now let's look at a mole of a gas.
How are we going to do that?
Well, because it's a mole party, I brought some dry ice.
Awesome.
Of course. So we are going to, like we had to add up the formula mass to get water's mole amount. Can we do that for carbon dioxide?
Absolutely.
CO2? Because dry ice is CO2.
Let me write that right here. I'm going to write it upside down if I can. Okay. Done this in teaching enough so that we can do this upside down on the old technology of overheads. But CO2 is made up of carbon. Each carbon is 12 grams. Okay. And then each oxygen is 16, so I've got 2 of those. Okay, we'll put our pluses in between there. So ideally, if we wanted 1 mole of carbon dioxide as a solid dry ice, then what we want to do is add these 3 up. So 12 plus 16 is 28, plus 16 is 44 grams.
Okay, so we need about 44 grams of dry ice, which is a solid.
Yeah.
In order to get a mole. So let's, could you turn the balance for me, please, and let's get 1 mole.
Okay, we've got the balances on. Let me tear that and take off the mass.
You ready?
Yep.
Whoops.
That's all right. No, you're doing good. You're about 15 grams there.
Okay. How about a little more?
Yep, we're going 44.
Another chunk.
Awesome.
38, a little bit more.
Yep, just a little more.
This is a little.
Oh, that's perfect.
Oh.
It's 43.9.
Oh, wait.
There.
Oh, wait, it's too much now. Let's get rid of some.
Okay. Well, you want me to just get a little...
Blow on it.
Oh, yeah.
Wow, look how fast that mass is dropping. It is doing, what is that called when it goes from a solid to a gas directly from one state to the next without going through liquid? We call that
yeah, that's sublimation. Sublimation is phase change from solid to gas. And we'll get a chance to see some other kind of phase change as well. And we're really close to being right on what we need, maybe a little less. But that would give you a really good idea of how much is in here.
So we got a little more than a mole of CO2 there. But if we left it there long enough, it would drop down to, it'll say 0 grams because all of the CO2 eventually would become and add to the moles of gas in the room.
We're losing 1/10 of a gram per second.
Well, you know what? Let's make this a real mole party and dump that into that beaker just for atmosphere here.
Ah, awesome.
But if we captured that gas, the dry ice escaping, we're looking at water condensing, right, from the cold air coming out.
Yeah, that cold carbon dioxide is coming up and cooling that air right around here, and that water that's in there is condensing.
Right.
From a gas to a liquid, we're getting condensing.
So we need a closed system if we wanted to capture just the carbon dioxide gas, so let's do that. Let's
there you go.
capture, we've got some sensors connected to JP's computer. Let's make sure that pressure sensor ends up in the beaker, just in case water splashes out.
Okay, they're both turned on.
So JP's computer, we're going to be measuring the pressure and temperature change over time when we drop the dry ice into this beaker. In a minute, Roger's going to take all of the air out of the bag so that we can be sure that anything contributing to the pressure and temperature is just CO2.
Yep.
And we'll monitor pressure and temperature. It'll take a few minutes, so we'll just leave it going once it gets going.
Perfect.
Okay, so I'm going to get another about 44 grams in here.
Okay. Ooh, 40 grams.
Close. You can start taking it out of the bag while I perfect the
Ooh,
mass.
that's really good.
Maybe I'll swap this piece for that. Go ahead and
There you
pull
go.
the air out.
Okay. Let me get down to low just this way. Okay. We'll close the straw off in here. Okay. If we go a little bit over,
Okay, and I'm still trying to get that perfect 44. I got about 45, so I think I'm happy with that.
okay.
Ready?
Yep, just a second.
Whenever you're ready. I had to close that dry ice because I didn't want us to suffocate because we don't want to replace all of the air in the room with carbon dioxide.
Okay, I've got it down pretty low.
Great.
I'm going to take a little bit more out after we put this in.
Okay.
Okay, you ready?
Ready? 1, 2, 3.
Nice.
And it's in
Okay,
there.
let me just take a little out.
Don't suffocate. Okay, so Roger's going to seal that bag up tight and we're going to let that dry. So you notice how cloudy it is right now. So there's some water vapor in there still, but a little bit. And that's going to keep going while we do some other demonstrations, and we'll come back to it. We'll look at JP's computer to get the data for that. In the meantime, let's do some more demonstrations.
Awesome. Let me put a little rubber band around there just to
triple check.
convince it, yep, to stay closed while we're gathering all this CO2 gas.
Okay, so I'm going to hit stop on SparkView, and we're going to go to a different experiment now. So you notice we've got some at-home. Do we need to hit start on the JP's computer?
Very good. I
Great.
missed a little corner here, so
Okay.
while you're explaining that, I'll retie up this little piece.
Okay, so this is an experiment your students can do at home to study moles, and moles in the reaction of vinegar baking soda. Is there a question?
There's a question.
Yes.
What model scale connects to SparkView?
How the scales? Okay, so we've got a
What
Bluetooth.
model?
Oh, I'm sorry.
We have a model. This is the Scout model. The Scout models from OHouse will connect, and so we've got two scales that fits on. But the Scout 400 is the one that measures 400 grams. The SKX, I think it's 400. So take a look at our scales there. The 200 and 400 have an attachment that just goes right to the computer.
Right. They can either connect with Bluetooth or USB as well. Okay, to get into SparkView. All right, everything's going on JP's computer. We're just going to leave that sitting there. I'm going to leave it off to the side. We've got stuff you can do at home here. Your students can use measuring cups, baking soda, and vinegar to do a little study in reaction stoichiometry, looking at the mole ratio of one reactant to another, and making predictions about what's the ideal mole ratio. Okay, so let's start with the first bottle here. You'll notice it says, you may or may not be able to see this, it says 0.02 moles. What that number is for the amount of baking soda inside the balloon. So this is only 0.02 moles of baking soda in the balloon. This balloon has 0.05 moles of baking soda. This balloon, 0.10 moles of baking soda, 0.15, and 0.20. I'm going to share the way that I got these numbers with you. I converted the teaspoons to moles by using mass. So I just took the mass of a 1/4 teaspoon and converted that to moles for your students, so it'll be easy to measure. Remind them that when they're measuring in chemistry, to use a level spoon or level scoop, so flatten out that teaspoon so that you don't have a heaping scoop of material. It should be a level spoon, and that goes for whether you're measuring baking soda or vinegar. So this balloon only has a 1/4 teaspoon of baking soda. That's where that many moles comes from, give or take. This has 3/4 teaspoon baking soda in the balloon. This is 1 1/2 teaspoon baking soda, 2 1/4 teaspoon baking soda, and 3 teaspoon baking soda.
And if you're at home, you may say, well, how did you change that to moles? Well, we just took the mass of it in the metric system in grams, and we calculated how many moles we had of each of these.
Right, using the formula mass of baking soda. So the bottles each have 1/2 cup of vinegar. That's the household vinegar you buy at the grocery store. It's 5%. And when you have a 1/2 cup of 5% vinegar, that works out to 0.1 moles of vinegar.
Vinegar you've seen as acetic acid or hydrogen acetate at this point of the year. At the end, if you're studying chemistry, you may learn it as acetic acid.
So the first bottle, the mole ratio is 0.1 moles of vinegar to 0.02 moles of baking soda. Let's get that going.
So that's a 5-to-1 mixture. 5 parts
5 vinegar,
vinegar to 1.
1 baking soda. And the next one is the next
Okay.
card.
Let's move that.
0.1 moles vinegar to 0.05
Okay, so
moles.
it's 1 to 2.
So you might have your students predict which one's going to get the biggest.
1 vinegar to 2 baking soda.
The next one with 1.5 teaspoons of baking soda.
Okay, so that's 1 to 1.
I think I need to make more space. That one's going pretty fast. Okay,
Okay.
next. This is 0.1 moles of baking soda. Uh-oh, it's going inside the balloon. That's not a problem. I can just
Tip it back out.
push it up.
Okay, now I flip this fraction so that we get the smaller number on the top.
Okay.
Okay.
And
so
the
it's 3 to 2 in that ratio.
these are just the 16 milliliter, 16 ounce, 500 milliliter bottles of water. or you could use larger bottles.
And as you can see, this is the preferred method of making volcanoes in science projects when you're really younger.
So your
There we go.
students might predict that the largest balloon would be the one with the most baking soda, since the one thing that's controlled here is the volume of vinegar, or the moles of vinegar is the same. They might have predicted that that one would get the biggest, but you can tell visually that the last 3 have the same size.
In importance, chemists wanted to study these kinds of materials to see what ratios they reacted. And remember how we said this is 5 to 1. This one is 1 to 1 baking soda to vinegar, and this is now 2 to 1. But what scientists realize is now we have no more change, so the best reaction ratio is 1 to 1. And when scientists started studying these, they realized all reactions were very simple, 1 to 1, 1 to 2, 2 to 2, or 2 to 3 kinds of things. Never that, simple whole ratios is what was studied. And this is how they started to understand reactions.
Right, so if your students can use this ratio of 1 to 1 to recognize that in the balanced equation for baking soda and vinegar reacting together, you need 1 mole of baking soda to 1 mole of vinegar. If you have more than 1 mole of either baking soda or vinegar, whichever there's more of beyond the 1 mole in the ratio, you're going to have excess.
Yeah, I can see it's cloudy in this one as well. There's some material on the bottom.
Extra baking soda in these 2, so those are the excess reactant. And here it's clear, but there's no extra baking soda, but it's the same size as the other balloon, so this is the perfect ratio. This is ideal,
And those
stoichiometrically.
2 down there, we're going to have extra vinegar. I mean,
Right.
the baking soda reacted, but the vinegar's still left. There's still some in there.
So the vinegar in this case would be excess, and the baking soda is limiting. Okay, so that's something you can do at home, and I have up on my screen right now on my computer just the procedure that I went over. And this is, so it's everything I said out loud. Okay, but there is a lab that you can do in the classroom with a pressure sensor if you wanted to do a quantitative analysis of the mole ratio in a reaction. I'm going to set these aside using the pressure sensor. So, I'm running out of room.
Yeah, let me take a few of these
Let's-
out
let's
of the
move
way.
these over here.
Absolutely.
Thank you.
Mm-hmm.
Okay, now this experiment is found in the Essential Chemistry lab book as well as the Essential Chemistry textbook. It takes some baking soda, this time in solution, and this time students are the ones who are going to figure out the moles. That we don't just give them the moles, that we give them grams, and we give them molarity, and we give them, and they have to determine the moles from there. So we've got 40 milliliters of sodium bicarbonate. Go ahead and pour that into the reaction. This is just a 500 milliliter beaker, or rather container.
Gas collection flask. Oh, there you go. Thank you.
Okay, it's a mole party.
That's right.
It looks like a party now. So we got this is just a 500 milliliter container, so you could use an Erlenmeyer flask, or even if you have a bottle of drinking water, a number 6 stopper often fits on top of that. So we've got citric acid here. It's 0.1 gram. We're not going to put in just yet because I want to talk quickly about the pressure sensor. Okay, so the pressure sensor is wirelessly connected to SparkView, and this is a number 6 stopper with 1 hole and some tubing to connect it. What we're going to do is we're going to work together. So I'll hit start on SparkView, then I'll dump in the solid so that Roger can quickly close the bottle, but he's going to try and not squeeze the bottle because that will affect the pressure. He's just going to make sure that that stopper stays on while these two things react. Let's watch and see what happens to pressure when we react citric acid, the solid, with baking soda. Okay. Let me get SparkView set up here, and I'm going to start collecting data. And 1, 2, 3, close it, and we're going to swirl like just like that while the reaction's going. And let's watch the pressure in SparkView. You can see the pressure is responding immediately, increasing. And we're going to do one run with 0.1 gram of citric acid. The second run will be the same experiment, but with 0.2 grams of citric acid, and students will figure out how many moles that is. The third run would be with 0.3 grams of citric acid, and 4 grams, and 5 grams. So they would get pressure data for each of those amounts of citric acid and figure out, similar to this, let's look at the pressure data to see where was the maximum product form, and call that the ideal ratio, and figure out how many moles of citric acid is ideal to react with the amount of moles of baking soda.
And relating it back to the previous experience, we already saw that it's 1 part of acetic acid or vinegar to 1 part baking soda. Here we've got baking soda, we're adding citric, and we're going to find out what's the right ratio.
Right, and it looks to me like it's slowing down. That might be leveling off already.
Yep.
I'm looking at the pressure in the live reading on the bottom left, and it's there, it's done. So I'm going to hit stop. Go ahead and open that flask. You might have heard a little bit of pressure
There's
release.
just a little bit of gas that came out there, am I right?
And so, like I said, we also have the students collecting 0.2 grams, which we've previously collected here on this run. Look at that pressure data on SparkView. You see how it's double the product. We got double the pressure change.
So there's still enough acid to react with the carbonate that's in the solution down there.
But the reaction went faster, as you can tell by the slope or the steepness of the curve. And then we did 0.3 grams, and then we did 0.4 grams. And we've got 0.5 grams here. And you can see on the last 3 runs, all 3 of those last runs show maximum product form. We're not getting any more pressure even though we're adding more citric acid.
So like these balloons, when we started with the just at home experiment, we saw at some point we don't get more gas to react because we've used up all of the acid, the vinegar. In this case, again, the first time we put a little 1/10 gram in, it didn't react all. 2/10 of a gram still created more gas than 3/10. But after that, we didn't create more. So we met the 1:3 ratios of the citric acid to the vinegar. Citric acid has 3 hydrogens. It's an acid with 3 H's.
So when students do the analysis, they go through and calculate the moles. We walk them through they mathematically calculate that 3-to-1 ratio using the grams they started with way back in the beginning.
And really, in the 1800s, this would have been your job as a chemist, is to go through and figure out how different things react with one substance. Then they'd switch to another substance, and they really learned everything we know about the periodic table when they did these comparative reactions.
So if you like this mole-to-mole experiment, you can go to the PASCO's experiment library. It is experiment 8D, determining limiting reactants.
And I'm going to step off stage and let JP come back in and finish up here.
Okay, so let's get back to JP. Let's go talk.
That's been quite a party.
I forgot the mole beach ball, the mole of air in the beach ball. Oh, but
we could have done a lot of things because this was really quite a party that we've been having with moles, and we're really very thankful for Roger. But let's take a look at some of the things that you said up here. You put in a mole of dry ice, and this bag was inflating. The really interesting thing is we can take a look at this, and I want to take a look at what I was collecting on my computer as far as the data is concerned. And I can see some very interesting things happening. I see that the temperature dropped. Of course, we would expect that. It was dry ice. It would go down. And the pressure, it doesn't look to me like the pressure really changed at all. And it's mostly because and my guess is going to be here, and no fault to Roger, but Roger, I don't think you tied this off tightly enough, because to me it's not looking like this bag inflated the way that it should. But that's okay, because we've got something to show you just in case yours does as miserably as this one did. But the interesting thing here is that if this would have filled correctly and this bag would have been nice and full, the bag would have had a volume of, and this is no estimate, 22.4 liters. And how do I get that number, Barbara?
well, that's Avogadro's constant. That is the volume of a gas at STP. And actually, since we're not at STP here, or a little warmer than standard temperature, we're not 0 Celsius in here. It's kind of probably like 25 degrees in here. It's pretty warm Celsius. So that is the volume of 1 mole of any gas at those temperature and pressure conditions.
Right, and so that would have been the volume of this bag, and it would have been actually complicated to measure because it's an unusual shape. So Barbara, you did something that makes this a little bit easier. Again, something you can do in the classroom, something you can do at home to figure out how much a mole of gas occupies. What did you do?
Well, I got a punching balloon, and I made this little contraption out of the top of a soda bottle that had a kind of a wider mouth. And I used this to help me drop some 44.01 grams of dry ice into the balloon, and I sealed it. And I took a video because it took 2 hours for that solid dry ice to sublime into
wow, 2
gas.
hours.
2 hours in a
Really?
sealed balloon of dry ice expanding. Let's watch a video. And Glenn, my colleague, helped with this video, so check it out. There's the balloon inflating. This was a time lapse over 2 hours. You'll notice there's the snow on the bottom. There's ice on the outside of the balloon. That is frost forming from the water vapor in the air freezing to the outside of the balloon and then falling off the balloon. So let me get to the, here's the part where Roger and I measured the circumference of the balloon. And we measured the circumference because we could plug that into the volume formula and get the volume of the balloon. It turns out that this balloon, and let's see what we came up with the circumference here, was very close to 42 inches circumference. So when you plug that circumference into the volume formula, that's about 20.1 liters.
Oh.
Which is less than we expect, right? But
Yeah.
remember, that's a balloon, and balloons,
Right,
they do
the
this.
balloon has its own elasticity and
Yeah.
it's compressing a little bit, so it wouldn't be the free volume, but something very close. Even just in a balloon, you're getting very, very close to that 22.4 number that we would expect at STP. Now, something neat happened that never happens here in Roseville. Maybe, I know I've lived my whole life, but I don't think I've ever seen this happen in Roseville. It snowed. That's right.
It snowed in the building.
It snowed in the building, right.
So we took a close-up of that because it was so cool. Here it is.
Wow, and if you look at that, you can actually see the snow crystals are
They're falling.
forming as they would in the clouds, and you can actually see the little snow particles dropping off of there. So it was
Yeah.
snowing on Barbara's desk. The fun things we do here at PASCO Laboratories, the excitement just never ends as we continue to explore some of the great things that we're doing here, including some of the wonderful stuff that we're doing here with moles. And you think this party was exciting? I'm going to give you kind of a little teaser of what's coming up next week, because we're not just having a mole party, we are bringing moles in as we have a Halloween party. Barbara, what's going on
That's
next
right.
week?
It's going to be the spooky edition of PASCO Live. In fact, it's PASCO Dead.
The
We're-
PASCO Dead.
PASCO Dead show. So we will be bringing lots of Halloween demos. There will be fire and lots of sensor-based, quick, fun demos that you like doing for Halloween, and also some data analysis and using sensors. And
Awesome. That
nerds.
sounds like a great party. So that's our little teaser for next week. But remember, you've been watching us this week, and I told you that if you joined me today, I would give you this great opportunity to get 5% off the different sensors. What did we see in sensors here?
Sensors
Barbara,
was-
what did we see? We saw
Pressure sensor and the fast response temperature sensor.
the pressure sensor and the fast response temperature sensor, great sensors that you can use both in the classroom, or if you're doing this from home or your students can use them at home, a great opportunity that you can then use these things to do that nice demonstration. Oh, and
The mole set.
you want to include that in the 5%?
Sure.
All right, Barbara included that in the 5%. You can get these mole cubes and these sensors 5% off until the end of October 2020. The end of October 2020, 5% off. And how do you get that 5% off? You contact our mole, inside mole here. We've got a mole in PASCO Laboratories, and the mole is Isaac. And you reach out to Isaac, and what was our word for the day?
I forgot.
P
Party.
for, how could you forget the P for party, right? We had a party. You contact our mole and say, I want to party with you, and he's going to give you 5% off the sensors that you saw today and that great little mole cube. And remember, if you're not with us here in the United States, that's fine. These things are all available to you because you can be any one of our 100 partners that are outside the United States, and feel free to contact them and get an opportunity to do any of these great opportunities that you saw here. And so we want to thank Roger, our mole expert, Roger. We want to thank Barbara, our mole expert, and we want to invite you to our Halloween party next week. But until then, we wish you the best of luck, best wishes, and great teaching. Good day.